So you are welcome again. We start. So today we'll be looking at introduction to inferential statistics. And you know, the first 3 days we talk about basic concept of statistics, descriptive statistics, then yesterday probability and normal distribution. Today we'll be going to introduction to inferential statistics. I think after today, we'll be able to go to specific tests because today we look at introduction to inferential statistics, then some assumptions around hypothesis tests. So maybe by tomorrow, we'll start with hypothesis tests, per se, fully into inferential, and we start with chi-square. Yes, let's move further. So there are 3 kinds of lies: lies, damn lies, and statistics. This is word of Disraeli, the former Prime Minister of the United Kingdom. So what he's saying is that if you don't know your statistics very well, you will tell lie, both intentionally and non-intentionally. Though a lot of people, because of their ignorance, they tell lie unintentionally. But and because they don't have the knowledge of statistics, there are some people they may know statistics, they still tell lie. Though sometimes also some people they deliberately cook data, they tell lie. So statistics can tell lie. You can use statistics to tell lie. And as you go further, you see the reason Disraeli said that. So now we talk when in the first day when we talk about the logic of scientific reasoning. I made mention of inference when I talk about deduction and induction. So I made mention of inference. I say inference is the generalization made about a large group or population from the study of a sample of that population. So, for example, now you quote somebody, found that 30% of the market women in Imo State, they will even say Southeast Nigeria are obese. Whereas this person study, yes, Imo State is Southeast, study Imo State, and now selected market, maybe one popular market or 2 or more market, and sample some 400 women and carry out the study. And the next thing they publish, you see it in journal, international journal, a study done in southeastern Nigeria. Shows that, in fact, for the fact that it's Nigeria, said the people will assume that 25% of Nigerian women, market women, are obese. That is generalization. From the sample about the population, that is inference. So this inference can be two. There are 2 types, either inductive or deductive. As we said before, when you talk about inductive, you go from specific to the general. We make observation, discern pattern, a pattern, make a generalization, and infer an explanation. That is inductive. What he's trying to say is that you didn't start this study, you didn't start with theory or hypothesis. You just carry out your study through, observation just means you collect data. You've collected your data, and you now begin to, when you run an analysis, that's, there's an association between this and this. So that association between that is like you are trying to develop a theory, an hypothesis. So that is why descriptive study does not test hypothesis, but it can generate hypothesis. So it is in descriptive study, you just go, there's nothing in mind that, there's an association between this, and you just do your work, and at the end of the day, you discover there's some association between some pair of variables, which somebody can, is an hypothesis now. Somebody can now go further, conduct another research to prove if it is true or not. So You that just did your study, there was nothing in mind about hypothesis. Whatever generalization, because you have taken sample, whatever generalization you are making that study is what we call inductive inference. Induction. Because from the general, you are, your generalization is suggesting some form of hypothesis. Whereas the person that pick your study and I say, oh, study has shown that so women are more likely to have this. From the what you have done before, they read in the literature, they now say, is it actually true? They now design a study where they now have an hypothesis. There's an association between this and this. There's no association between this and this. So from the inception, they set out to test an hypothesis. So whatever generalization, by the time they finish the study, he said that the hypothesis is true or not. Of course, it's a form of generalization to the population. That is deductive inference. So in deductive inference, we hold a theory, and based on it, we make a prediction of its consequences. I.e., we predict what the observation will be, as in the case of hypothesis testing. Let's now look at, that's just short one on inference. So in inferential statistics, if you remember, when we want to first of all talk about descriptive statistics, the first thing we say that the concept of distribution. We say, if you remember, the concept of distribution. It's the same thing. You want to talk about inferential statistics. The first thing you want to look at is sampling distribution. And you see, it's very funny. Sampling, what is sampling distribution? In the course of our lecture and workshop, we'll be talking about, in the last 4 days, we'll be talking about distribution. The second day, we talk about distribution, where we say there are 4 types: frequency, relative frequency, cumulative frequency, cumulative relative frequency.
Cumulative frequency.
Cumulative, yes, relative frequency. So you can mute. So now, yesterday also when we talk about probability distribution, yes, we talk about distribution also. You see, it's actually the same thing. If you know, in the probability distribution, I made mention of relative frequency approach, you remember? And I told you that when we're talking about discrete probability, continuous probability, I made mention of the percentage when you tabulate. It's the same thing you see when you tabulate your table, frequency table, you put percentage there. It's actually the same thing. But this one is the same thing in another way. What's meaning of sampling distribution? Is pattern of occurrence of sample statistics obtained from samples repeatedly drawn from one or more populations. What we are going to see here is, in the distribution we talked about before, the unit of sampling is one person. Imagine I want to know the weight of people. I can take sample of 400 people, and sorry, I was knock off by the network. Yes. So generally when we talk about distribution, the unit of sampling is individual. Then now we want to know pattern of occurrence among them, or the value of the variable in that data set. But in sampling distribution, what it means is that you take sample. We already said that when you take a sample in descriptive statistics, you take a sample and you summarize from collection of data up to summarization stage. That's descriptive statistics. When you summarize, you get a statistic, a value. So depending on the type of variable you are dealing with, Sorry. So, yeah, the in sorry. So, but in sampling distribution, I told you when you take a sample, you summarize. You either summarize in mean, mode, and median for quantitative variable, or you summarize in percentage or categorical. Whichever one, either it's mean, mode, or median, they are statistics. That is summary of sample characteristic is statistic. If it is plural, it's more than one, you can say statistics carry head. But with if it is only one, statistic, is different from the subject statistics that usually carry S. This one is only when it is plural, it carries S. That is, if it's you say the mean weight is 74 kg, that is statistic. If you say the proportion of female is 70%, that is statistic. If you say the infant mortality is also and so, that is statistic because it's from the sample. But if you now say in the population, what is the mean weight in the population? That is parameter. What is the percentage of women in the population? That is parameter. Can you see now? So the summary for sample is statistic, but the summary for the population is parameter. Now, what I want you to understand here is that that shows that anytime you take a sample, you end up for a particular variable, you end up having a summary, one for each sample. That is, if we are interested in the mean way, what is the mean way? That is statistic. So what this sampling distribution, what is the meaning of sampling distribution? Is that if you take sample many a time, imagine you take sample again, you take sample again. If you calculate mean weight to be this, you take another sample, it may not be exactly 75 kg, it may be 74. You take another one, it may be 76. You take another one, the mean you calculate. When we say you take another sample, it is not the same sample you took before. But some of the people that were in former sample may be here, but it's not completely the same. It's like in the population, you just take at random sample of 300 people, you summarize. You take another 300 people, you summarize. You take another. Let's say you do it up to 50 times or more than that, many a time. When you summarize, you get different value. Some of them may be the same, but you expect variation. That is, the pattern of occurrence of that value is the sampling distribution. Just like if you take one sample, you measure somebody's weight, each of them. If they are 50, you measure their weight and you look at you do the distribution of the weight. It's the same thing. If you take that is the ordinary distribution we talk about. But in sampling distribution, as you take sample, you summarize, you get mean. You say it may not be mean, it can be mean, it can be percentage, whatever is the summary. When you summarize, you take many. Let's say you take up to 50 times. The pattern of occurrence of that one is the sampling distribution. I don't know if you can grasp it now. If you have question with that, problem where you can let me know. You can chat or you can raise hand so that because it's very, very important. If you cannot understand this concept, you will not be able to understand the inferential statistics. Because that's the first thing you want to talk about in inferential statistics, the meaning of sampling distribution, pattern of occurrence of sample statistics obtained from samples repeatedly drawn from one of the population. Now, if you look at it now, when you take in sampling distribution, there's always sampling variation. What the meaning of that is, I've already said it. If you take many times, you summarize, you won't get the same thing. In some situations, you may get the same, but all of them cannot be the same. There will be variation. See, just like the way we are here in the class. If you want to look at our weight or our age, some may have the same, but it vary. You ask each person, will tell you the age, but some may be the same. Oh, you are 39, you are 39. It may be, all of you cannot be 39, cannot be the same. It's the same thing when you take many samples, you summarize. The value you are getting may not be the same if you take for all the samples. Some of them may be the same. So Because of that, there's variation. Now, just as the way you know that in normal sample, maybe one group now, you look at pattern of occurrence of value among you in the class now. You see that you can, since it's not the same, you can calculate the mean. You can calculate the standard deviation. It's the same thing in sampling distribution. Since the value vary, you can calculate the mean. Imagine that the statistic we are talking about, maybe mean weight. After you take sample many times, it gives you different means. You can calculate the means of mean. When you calculate the means of mean, that will be the mean of the total, all the means together. It is, and because you can calculate the mean, you can calculate the standard deviation. Because from the mean, each of those mean is standard deviation from the mean. So I'm just talking about mean. Mean can be just is mean if you are talking of quantitative variable. If it is categorical, maybe proportion of female in the class. Maybe in each class, you take maybe in the 9 university, you take some many time. We say in the 9 university, what is the proportion of female? You're going to get different proportion, from different sample. So that is percentage, not mean. But since it's different, you can calculate the mean of the percentage. That mean of the percentage is the mean of the sampling distribution. You can also calculate the standard deviation of that value of the sample statistic, whether it's percentage for categorical variable or is mean for quantitative variable. You can calculate the mean and because they are number. If you say 50%, is it not a number? Even though you are using it to summarize sex, which has no number, but when you say the proportion of female here is 50%. So 50% is number. So you can calculate the average of the numbers and calculate the standard deviation. Now it is believed that the mean of the sampling distribution, the means of those values of the sampling statistic in the sampling distribution is equal to the mean, the parameter. I don't know if you understand me now. If let's say by maybe the proportion of female in that university, let's say is 55%. Now, in that university, green one, that would be parameter because we are talking of the total population of that university. The proportion of female is 55%. It's just an assumption. I'm not saying 55%. If you take many samples, you will not get some. It can be higher than that. Some it can be lower than that. Based on you can get different value. If you calculate, you get all the value together, and now calculate the average. That average will be close if it's not equal to that 55. Can you see now? So the this logic is being used anywhere, even in the laboratory. If you want to get you want to measure something now, mass of something in chemistry lab, you want to measure, or in physics, when you measure something, you measure it many times, maybe up to 10 times, you calculate the average. Believing that because each measurement, you are not sure if you have gotten the real thing. By the time you measure it many times, some will be high, some will be low. When you calculate the average, you believe that that average should be the real value. Can you see? It's the same thing doing sampling distribution. So the mean, the average of that statistic is believed to be the parameter, the value, the real value you are looking for. So by the time we calculate the average of all the percentage of women from different samples, we now say, oh, the average of that one is 65%, which is the real value in the population, which is the parameter. Since you cannot know the parameter unless you attend to all the population, but it's difficult to attend to all the population, especially when population is large. Apart from that, when large, if we want to do that in the university, you cannot get it because everybody will not be present. You may say, oh, somebody is sick, he cannot come to school. This one travel is around. Even if you check throughout the year, you say you are collecting data, you want to attend to everybody, you will not see everybody. So that's one thing. So that's why you take sample. And once you take sample, it can never be equal. Whatever you get can never be equal to the parameter. So one way statisticians and intelligent people go about it is to say, okay, this concept of sampling distribution, if we are taking sample many a time and now calculate the average, whatever we get will be the free parameter we are looking. And since you can calculate the mean, you can calculate the standard deviation. The standard deviation of sampling distribution is known as standard error. The standard deviation of sampling distribution is known as standard error. Some people mistakenly say, what is? We have already said that. And that standard deviation, it is believed to be the standard deviation of that attribute in the population. That standard error, which is the standard deviation of standard distribution, it is believed it is equal to the standard deviation of that attribute in the population. Just like as we said that the mean is believed to be equal to the parameter in the population, then the mean, the standard deviation, which is the standard error now, is believed to be equal to the standard deviation of that in the population. But so that is why some people, when they ask them, what is standard error, they say population standard deviation. It's not true. It is believed that it should be equal to the population standard deviation. Standard error is standard deviation of sampling distribution, but it is believed it should be equal to the standard deviation in the population. It's not as if maybe that is the standard deviation in the population. You cannot actually know standard deviation in the population unless you take data from all the elements in the population. Just a minute. Sorry. Sorry, I just noticed. So sorry. Since when? Please talk. Since when?
Since before this slide come up.
Okay. Sorry.
Okay.
Sorry. Let me be sure that this thing is recorded itself. Yes, sorry. Let me go back. Yes, I think I talk about, I've explained sampling variation. I said that since you take sample many times, the mean will differ. If you calculate the average of the mean of those, well, it may not be mean. The statistic can be mean if you are talking about, it can be mode, it can be median when you are talking about quantitative variable. But if you are talking about categorical, it's percentage. Whichever way, both of them, all of them are statistics. Whichever one, either is mean, mode, or median you are doing, or percentage. When you summarize many times, it gives you many, no different for different sample, it gives you different value. When you now calculate average of that thing, that average is equal, is believed that is equal to the parameter. If what you are dealing with is maybe percentage of women or percentage of Christian, in maybe in our university. So that percentage of Christian, when you summarize for each sample, is number. So you have many value from all the sample you had, and you have to calculate the average. When you calculate that average, it will be a percentage. That, the average is so percent. It is believed that is the real percentage of Christian in our university. If it is me age you are talking about of the student, and you take sample many a time, and you now get different value, and now calculate the average of the value, it is believed that would be the mean parameter, which is the mean age of the student in the university. Does it make sense? So, and because you can calculate the mean, because there are different values, you can calculate the mean. You can also calculate the standard deviation. That is, how spread are the values. So when you calculate the standard deviation of the sampling distribution, it is called standard error. Standard deviation of sampling distribution is called standard error. And it is believed it is equal to the standard deviation of that attribute in the population. All those you are taking sample, you are not dealing with the whole population, but because you are doing more over and over. So if you calculate the average, it is believed that whatever you get as the average is equal to the parameter. And the standard deviation of it is equal to the standard deviation of the value in the population. Standard deviation also in the population is a parameter. Mean is a parameter. Anything you summarize for statistic is for sample is statistic, whether mean, mode, median, standard deviation, percentage, or whatever. But anything you summarize for the population is called parameter, whether mean, mode, median, or percentage, or standard deviation, or sensitivity, or specificity. Talk of anything you can calculate. Positive predictive value, negative predictive value. If you do it for sample, it's statistic. But the real value for population is parameter for anything. So you can see now, and I said something also, that because when you calculate the standard deviation of that sampling distribution, and which is called standard error, it is believed to be equal to the standard deviation in the population. Some people, when they ask what is standard error, they say population standard deviation. It's not true. The truth is that it is standard deviation of sampling distribution, which is believed to be equal to the population standard deviation. That's what I said. And I now gave this illustration. I said this illustration is just to give you, to summarize what I've just said. Illustration of standard error. Now, let's assume that this is a number of children. We are talking about, let's just assume this number of children in each family. So the larger circle where we have many families inside, you can see the family are plenty. They now say, okay, if the mean number of children in the population is 2, mu, if you remember, mu is the mean in the population is 3, rather, it's equal to 3. Now, if you now, this person now took 9 samples. This 9 sample contain each of them 4 families. In that contain the number of children, the now calculate the mean, divide by 4, calculate the mean. You can see the mean now differ. We have one of them is 1, 2 of them are 2, 3 of them are 3, 2 of them are 4, 1 of them 5. So all the mean now, if you calculate, you add it together, and now calculate the mean of it, it will give you 3. which is the mean in the population. And you see now, it's just an illustration. And that is what is plotted down here. How many has mean one? One of them. How many has mean two? Two of them. How many have mean three? Three of them. How many of them have mean four? Two of them. How many of them have mean five? One of them. And you see, so now you can see follow, you see that even that one, it follow normal distribution. We are coming to another thing. This will lead us to another concept. Now, I believe you understand.
Yes, sir.
Yes, sir.
You understand? Now, let's move further. Now, to be sincere with you, nobody will take, because you want to know standard error, sampling distribution. Now, we now begin to take sample many times. In the earliest day of statistics and probability, they do that. And it's easy to do, though it's difficult to collect sample in those days. You know, in those days, somebody say, as well as statistics, you want to ask you a question. Nobody had listened to you. But because these statistics grew through game of chance, so people go to all those Monaco, Monte Carlo, Monaco, all those places that they gamble. That's where they collect data. So somebody, you know, when you make trial many times, that's you are taking sample many times. So you know, gambler now, you are not the one that has to come and gamble. They come, they gamble, the same person will try many times. So that was how people, the early statistician, that's how they study statistics and probability. Now, nobody takes sample many times because intelligent people discover that, let's say you take sample many times, you calculate the standard error. You have discovered that standard error is standard deviation over square root of sample size. That if you even take the sample once and calculate the standard deviation, then put it over square root of sample size. Can you see now? What it means that if the sample size increases, the error will reduce. Just like if you take large sample size, your error of estimate will reduce. If your sample size is small, your error will increase. So that standard error, which is standard deviation of the sampling distribution or standard deviation in the population, is inversely proportional to the square root of sample size. So intelligent people have gotten that. So standard error is standard deviation over square root of sample size. Any question? Now, so we have tried that. If you have question, we want to go to another concept which is related to this. Is what we call central limit theorem. So you'll be hearing that normal distribution is the most important distribution in statistics and research because it is the basis for hypothesis test. And this is the reason. Central limit theory says that sampling distribution of certain statistics will approach normality as sample size increases, regardless of the shape of the sample population. You can see the diagram now. So this one is skewed. This one, the side on both sides, they are skewed. The other one is rectangular. They don't know follow normal distribution. That one that rectangular, you can see, is even followed by discrete binomial distribution. Look at the other one. So all of them, they are not normally distributed. What it's telling you is that even if the variable you are talking about is sex, that it doesn't even have number, sex does not follow normal distribution because it's not even a continuous variable. It's only a continuous variable that follows normal distribution. Even the continuous variable, for your data, you may not even follow normal distribution if the sample size is very small. There are some things that cannot follow normal distribution. Anything categorical cannot follow normal distribution. But it has to be something continuous. Even this discrete will not follow normal distribution. It has to be something continuous. Even the continuous, why some of them will not follow normal distribution if they are outlier and if the sample size is very small also. Sometimes you need up to about 30, sample size about 30 or 31, above 30. for something that normally follow normal distribution to even follow it. So what central limit theory is now saying that it's not talking of the distribution of that, but they are sampling distribution. I think you've understood the meaning of sampling distribution. So their sampling distribution will follow normal distribution if the sample size increase. So what it means that, let me give an example now. If someone want to know the percentage of female, like what I say in our school, you know that even female says is either sex is male or female. But when we summarize it, we say, okay, percentage of female, this is percentage of female. Since it's number, if we now take sample many a time, sampling distribution, this is number. What is the sampling distribution of that sex of female, maybe proportion of female, will follow normal distribution, especially if the sample size is large. I think the sample size you take for each of those samples is very big. The sampling distribution will follow normal distribution. So what he's saying now is that the same thing with even the normal distribution itself, of course, will follow normal distribution. So any distribution, you get to know later. When we talk about chi-square, theta, all of them, as the degree of freedom increases, sample size increases, they will follow normal distribution. So normal distribution is like something hidden. That is everything. Even all those ones that are not, there are conditions that make them to behave like normal distribution. Even for those things that look as if they don't follow normal distribution, their sampling distribution follow normal distribution. It's just like we dress ourselves. We say this one is important dignity. This one, we are all human beings. We would say, this one is educated, this is a local person. Then if you look at anatomy, everything, look at physiology, everything, we are all human beings. It's just just covering ourselves. If literature come now, someone that I think is a senator that maybe with Gregala, if they say they throw pump down, it will run the way we join. It can even join the fence. You now know that yes, it's like any other person. So this is just a summary of central limit theory. With this, we'll be able to know why normal distribution is the most important distribution in statistics and research, because it's the basis for hypothesis testing. So this one is just illustrating it also. You know, look at this graph that is red. So if you increase sample size, it can change to normal. This one that is purple. This red is not normally this red, is skewed. But this one that is purple is the normal distribution. This one gets transformed to this. That's what you now see, especially as the sample size gets larger, especially if it's greater than or equal to 30. Now, we have settled two concepts now: sampling distribution and central limit theorem, which are very fundamental for your understanding of inferential statistics. Now, let's go to the inferential methods. There are, up to date, I think there are up to 4 inferential methods, but the commonly used one are these two: hypothesis testing, confidence interval. We have Bayesian statistics based on Bayes theory, and it has link its root in probability also. So, and we have this Monte Carlos also. But those ones, they are not. No, Bayesian statistics has been there for long, but people do it, but it's not coming up now. But the most commonly you want to discuss is hypothesis testing and confidence interval. Now, let's what is. When we talk about hypothesis testing, all these test statistics you had of chi-square, theta, and over, all of them are hypothesis tests. They are hypothesis tests. Then we will now differentiate between those one and confidence interval. When we talk about hypothesis testing, it's a method of decision making. The decision here is it relates to the choice between two competing, mutually exclusive statements regarding one or more population parameters. The completing statement of fact are referred to respectively as null and alternative hypothesis. It's a statement of maybe relationship between two variables. But this statement, they are stated in two ways, mutually exclusive. That is, the meaning of mutually exclusive is that if one is true, the other one cannot be true. So, for example, now you see there is an association between salt intake and blood pressure. That is, if as the salt intake vary, the blood pressure will vary. There's an association between salt intake and blood pressure. That is what we call alternative hypothesis. There's no association between salt intake and blood pressure. That is not hypothesis. None, there's none. Actually, this first one, the one they say there's association, is actually the hypothesis. Research hypothesis. Okay, now you that you are studying, you want to study something. You are looking for relationship or association between something. Oh, is there any link between these two things? That's what I want to study. So there's association between this and this is the research hypothesis. That's what the researcher is interested in. But the statistician that will help you analyze it, for him to be able to do it, he has to state it in his own. Statistical hypothesis is the non-hypothesis. There is no association. It's the statistical hypothesis. Why there's association, which they call alternative hypothesis, is the real research hypothesis. So why is it that statistician cannot prove? Statistician cannot test alternative hypothesis. It can only test non-hypothesis. You know, the alternative hypothesis say there is an association. Now, if you say, okay, before I move further, this non-hypothesis and alternative hypothesis can be stated in another way. Instead of using the word association or relationship, you use the word difference. Mind you, when you are saying there's an association or there's a relationship, you are talking about association or relationship between two variables. For example, salt intake, blood pressure, they are variable. Salt intake can be what amount of salt you take, or much salt or little salt. Or your blood pressure may be the measurement of blood pressure, or your hyper is high or is low or is normal. Now, these are two variables, salt intake and blood pressure. Now, if you want to say there's a difference, you say you have to now know, because as you say salt intake and blood pressure, by using the word association or relationship, you don't even need to bother which one is depend on which one is dependent variable or independent. You don't need to know, but you don't need to say it. You may need to know, but if you have to use the word different, you have to know which one is outcome, which one is expression. So when you are talking about association between two variables, one must lead to the other. One must lead to the other. The one that leads to the other is the exposure or independent variable. The one that something lead to is the outcome or the dependent variable. Let me explain it again. Now, between salt intake and blood pressure, which one leads to which? It's not blood pressure that will lead to salt intake. It's the salt intake that will determine the blood pressure. It's not the blood pressure that determines your salt intake. It's your salt intake. So most of the time, that particular thing that leads to something is what you have control over. What the thing lead to, you don't have control. For example, now, a man cannot just say, okay, let me open my artery and regulate my blood pressure. No, but it can limit. Say, I will take more salt, I will not take more salt. But the blood pressure is as a result of the amount of that salt. If you want to stop the blood pressure or regulate it, you have to regulate it through what you can control. The same thing, if you say female pregnancy, socioeconomic status. Socioeconomic status may be the one determining female pregnancy. Now, let's just stick to that salt intake and blood pressure. So when you want to use the word different, you must be able to know which one leads to which. And mind you, the one that, for example, salt intake now is an exposure variable. Blood pressure is the outcome variable. But you can call the salt intake exposure variable independent variable, while the other one is dependent variable. The word independent and dependent is from the people that have been involved in experimental research, while the word exposure and outcome people that have been doing observational research. But they know that they are doing the same thing. Somehow. You know, in experimental research, you have to, for example, now, if you want to carry out experimental research for salt intake and blood pressure, you say, okay, you say some people should not take much salt. You discourage them from taking salt, and you leave the other people to be taking their normal salt the way they are taking. So those people that take less salt, you want to see, you now measure their blood pressure to both of them to see if the blood pressure is higher among those that you left to be taking their salt like that, and lower among the people you say they should reduce their salt. So in that situation now, the whether your blood pressure is high or low depends on which group you determine you belong to. That's why that blood pressure is the dependent variable. The salt intake is not dependent on blood pressure. That's why they call it independent variable. So that exposure variable is independent, while the outcome is the dependent. But it means the same thing. It's just a matter of nomenclature. So exposure or independent variable leads to outcome or dependent variable. And this exposure variable, they can call them factor, they can call them predictor. They are different names. You can call them determinant. No, that's why I say, what are the risk factors for hypertension? What are those things that can lead to hypertension? Risk factors, determinant. So when you are doing your research, you say, you want to know the prevalence of hypertension, you want to know the determinants of hypertension, or the risk factors of hypertension, or you can say the predictors of hypertension. They are all exposure variable. While the hypertension you are talking about is the outcome. They are all independent variable. The hypertension is the independent variable. I think it's very, very clear now. Now, when you want to use the word difference, you will not say there's a difference or there's no difference in the outcome variable. The outcome variable is the blood pressure between the different categories of the exposure variable. You can say there's no difference in the blood pressure between those people that take high salt intake and low salt intake. There's no difference. There's no difference in teenage pregnancy between the low and high socioeconomic class. There's no difference. Or there's a difference. There's no difference is not hypothesis. There's a difference is alternative hypothesis, which is research hypothesis. Or there's a difference between, there's a difference in the blood pressure between those who that take much salt and people that don't take much salt. Or there's a difference in the rate of teenage pregnancy between teenagers from low and high socioeconomic group status. Can you see now? So when you are using the word different, you are quoting the difference in the outcome. You must be able to know the outcome or the dependent variable. If you don't know, you make blunder. Some people say there's no difference between hypertension and salt intake. It doesn't make meaning. There's no difference between salt intake and hypertension. No. Say there's no association or relationship between salt intake and hypertension and blood pressure. Or if you want to use the word different, there's no difference in the blood pressure between those that take salt, much salt, and people that don't take much salt. I think it's very clear. So, and I've already told you, the null hypothesis is the statistical hypothesis. The alternative hypothesis is the research hypothesis that the researcher want to test. Why is it that the researcher cannot test alternative hypothesis? If you say there's a difference between my age and your age, the next question is, what is the difference? And there are infinite number of ways my age will be different from your age. It can be different by 1 year, 2 years, 3 years, 4 years, 1.5 years, 1.25 years, 1.2 years. Infinite number of ways. 1 day, 2 weeks, 3 weeks, 3.5 weeks, 2 points. So there are infinite number of ways two things can be different. So if you now want to test it, you have to be testing infinite number of hypotheses. because they say there's a difference. So that is why the statisticians say we cannot test this. They now look for a competing, mutually exclusive way. Now say there's no difference. If you say there's no difference between my age and your age, you say there's no difference. So there's no further. That is the same. Of course, if the null hypothesis is true, the alternative hypothesis cannot be true. And if the alternative hypothesis is true, the null hypothesis cannot be true. So all you need to test the null hypothesis. Once it is not true, that shows that the alternative is true. And you see now, that is the logic. So the research hypothesis is what is the alternative hypothesis that the researcher want to know. But the statistician that will help you do it can only test null hypothesis. That's why now I change it and now state the null hypothesis. That is why in research, actually, all you need to do is your research hypothesis. It implies that the statistician will use the null to calculate, but some people just write null hypothesis the same statement as if you don't have thing to do. So stating the two is amateurish. But I'm not saying you should not take the two, because sometimes if you don't say, some examiner will say, no, you have to state your null hypothesis. Let's see our alternative hypothesis. So sometimes when you are writing exam, you must play to the gallery. You will even be good, they fail you. The person that done rubbish thing, they may pass. In as much as the person that done rubbish thing, the examiner is as stupid as that person, you will pass the person. And you that will have done the right thing, they will fail you. And that is why I'm just giving you the clue so that you have the logic, you understand the logic behind it. Now, the step in testing hypothesis will leave it, you get to know it later. That one is not a big deal. Because if I begin to see the step, it will be confusing because the terms there, you will not understand, but you will get to know it as we finish this. Now, the logic there is that you state your hypothesis, not hypothesis, and to test your research hypothesis, and you gather data. So if by the time, you have already stated no hypothesis, that's what you are testing. And in real life, no hypothesis can be true, it can be false. You know what I mean by that? You say there's no association or relationship between salt intake and blood pressure. That's what you want to test. Is it actually true or false? In real life, it's only God that knows that statement. If it's true or false, it's only God. And any of them can be true. So the two possible outcomes of that statement is either it is true, no difference, or it's false, there's difference. That is the vertical, on this table I'm showing you, that is the vertical, the column. Not hypothesis, true, that is, there's no difference. False, there's difference. Now, when you do your own research, you are going to conclude, have your own conclusion. Based on what you see in your data set, the result you see, you will say, oh, I'm seeing a difference, or I can't see any difference. Can you see now? So if you see a difference, say, I reject no hypothesis, so I can see a difference. So if you didn't see any difference, instead of this, say, I accept, they say you should not say, you say you fail to reject. I will tell you the reason you should not say you accept. Because I will tell you later. So, but you say you fail to reject. That is, there's no difference. So you can see now, even your own study, there are two possible outcomes. It's either you see a difference or you didn't see a difference, you don't see a difference. Why the null hypothesis in real life? It can be true, it may not be true. Two possible. So when you cross-tabulate the two, it gives you 4 mutually exclusive outcomes. And these are the things you saw on the table. Now, it is possible for you, there's no difference. In real life, there's no difference. And your study say, I can't see any difference. So let the sleeping dog lies. In real life, no hypothesis is true. There's no difference. In your study, you say, you fail to reject you, there's no difference. That's why in real life, there's no difference. Your study says there's no difference. So you are correct. There's nothing. In what he's saying now, another way of talking about this is there's no association. So the hypothesis says there's no association. And your study says there's no association. That's all. Nothing. Everybody go on his way. But it's very bad many times. People don't want, if you do research, especially research for either publication, even for exam, If you don't find something, it's waste. It's not actually waste. If you set out to find something, you are not sure. That's why you are finding it. You will not find any association. But some people will say, that shows that this study you have done is waste. No. So that's why people cook association. You are correct in that. If in the real life there's no association and your study, you don't find association, that's a correct decision. Now, another one, that's a concordance now, in the sense that no different, no different. No different, you don't find different. It's possible also there's a different. That is, no hypothesis is false. And you find a different, you reject no hypothesis. So no hypothesis is false, there's a different, and you find a different, you reject no hypothesis. You are correct also. That is power of the study. So power is the ability of the study to find a different. If it's there, there's different there, and you find it. That's the power of it. It's a correct decision. Those two decisions along the diagonal, they are correct. But the other two decisions, which I put type 1 and type 2 error, those are the wrong decision. Is it wrong decision? Yeah, wrong outcome or whatever. The first one, that's error. There are two errors, possible error. So out of the 4 different options, 2 will be correct, 2 are error. I've talked about the 2 that are correct. Now, let's talk about the 2 that are. Type 1 error is when there's no difference in real life. And your study says there's a difference. It's like a commission. You are committing yourself. There's no association between anything, these two variables. But you say, there's a found association. That is type 1 error. Rejecting no hypothesis when it is true. No hypothesis is true, there's no difference, but you reject it. You say there's a difference. Reject true. Can you see? Rejecting no hypothesis when it is true. That's type 1 error. Now, there's another one. Second one. When there's a difference, your studies, I didn't find anything, no difference. That is not rejecting no hypothesis when it is false. No, but the mnemonic to you to remember is rejecting true. Rejecting when it is true. Just one word, when it is true. Rejecting when it is true. Not rejecting when it is false. Not rejecting, not is false. Rejecting when it is true. So rejecting true is type 1 error. Not rejecting or failure to reject no hypothesis when it is false is type 2 error. It's like omission. Omission. There's a difference that you say there's no difference. So each of those errors have their own implication. It depends on the situation. In law court now, it is better you make type 2 error than type 1 error. Type 2 error means that, this person commit this offense, but you say there's no offense. With all the evidence, there's no evidence against this person. And the person is a killer. He's the one that committed murder. It is better to do that than to say, type 1 error. This person was not the killer. They say, with all the evidence, they are sentenced to life imprisonment for hanging. And that person did not do. It's more grievous. It's with them. So it's better you set an offender free than to sentence an innocent person. In that situation, it makes the type 1 error to be more grievous than type 2 error. Though there are some situations where type 2 error may be, for example, now, there are some metabolic problem that if you can diagnose it correctly, you save the life. Simple way of saving. It's just for you to diagnose. All this, so you that are doctor, you remember spot diagnosis. There are some life-threatening situation that if you can diagnose it, even the treatment is simple. So omitting it is an offense. It's a big offense. So in that way, type 2 error is a big offense. For example, that's why they film people in medical school. They say there are some things. You see scabies. Is it spot diagnosis? You expect to know, this is scabies. Or rabies, case of rabies. Or many things. They expect a spot diagnosis, just see it, you see it. If you don't, they can even fail you in exam. For you not to, they say you fail. Because in that situation, the type 2 error is very grievous. This metabolic problem, phenylketonuria. If you miss it, It's a metabolic problem. If you can get it, you can easily save the shadow, that of the shadow. But if you miss it, but grievously in statistics, I think type 1 error is more grievous because, for example, now, if you are doing study on a drug, if there is a difference in and you miss it, another person can do the work and get it. But if there's no difference, you say there's difference. That's type 1 error. If there's no difference, you say there's a difference. It's a grievous something. No, it's a grievous. It's just like cancer, someone that didn't have HIV. You see, the error say you have HIV. Some of them die even before for the fact that they hear that they had cancer. That's one that's already sentenced them to death. Psychologically, they die. So it's better you even if somebody have cancer, some cancer that you even no treatment, it's better you miss it because at least the person will still live sometime. But if the person didn't know, the person will even die. You die by the reason of your diagnosis. That's just the. So now I want to type 2 error. If you look at it, if we are to tabulate now and put total below, if you put each of them is total is 100%, type 2 and that power, they will be up to 100%. So type 2 is opposite, like a complementary to power. If your type power is 80%, your type 2 error rate is 20%. For instance, if your power is 90%, your type 2 error rate reduce to 10%. Now, let's talk about type 1 error. So, sarcastically, I usually, they say, though in the real sense, you can only make one out of the 4 decisions. Sarcastically, they said one king committed the 2 errors at the same time. How? They say that the king has two servants, male servants, one answer, one not answer. And I suspected that one of them was sleeping with the wife. So he just erroneously believed that it must be the handsome guy that is doing the havoc. Whereas it's the one that is not handsome that is doing the havoc. So he sacked the handsome guy and promoted the other one. So he committed the 2 errors at the same time. So now, let's talk about that type 1 error. Very, very important statistic. The probability of committing that type 1 error is the p-value. Heard of p-value, p. The probability of committing type 1 error is p-value. P is probability. We have already said that probability is from 0 to 1. So now, if I ask you now, if the probability of committing type 1 error is p-value, if the probability is 1, I want you to talk now, you can unmute and talk. If the probability is 1, what does that mean? If the probability of committing type 1 error is 1, what does that mean? If the probability is the p-value, but if the p-value now is 1, what does that mean? So I want you to respond. Because there's something you want to trick your brain. Nobody. The probability of committing type 1 error is the p-value. If the p-value is 1, what does that mean? What does it mean?
It means there's 100% of chance of there's a certainty that the error
is certain you are committed. Yeah, you're right. Who is talking? Who is talking? Who is
Farouk.
talking? Okay, Farouk. Yeah, well done. So you are right. You are 100%. You have committed. It's certain. It's certain that there's no difference. You say there's difference. That is what it means. There's no difference. You say there's difference. That is your p-value is 1. Well, what if the p-value is 0? What does it mean? What does it mean if the p-value is 0? Because it can be between 0 and 1. If it is 0, what does it mean? The probability.
There is no error at all.
That is, you started that you have not committed the error. That is, you have not, that's what that is true that you say there's a difference because you have not said there's a difference when there's no difference. You are correct, there's a difference because you have not said there's a difference when there's no difference. Can you see that? Why the other one, if it is 1, When there's no difference, you say there's a difference. So in real life, the probability can be 0, the p-value can be 0, it can be 1. Though some people are saying it cannot be, it can be 0, it's probability. Because many times when you calculate it, the machine give you 0.000. Yeah, it may be true that decimal, maybe up to about 9 decimal places there, the computer cannot give you that. So that's why we want to write now, say, if you give it 0.000, you just say less than 0.001. You just look for one extremely small value and say less than that. But since it's probability, it can be 0. It can be 0. So it can be 1, it can be 0. But most of the time, it will not be 1, it will not be 0. It will be something in between 0 and 1. And that's something in between 0 and 1. Let me see if I can use pen. Pen to write. So you can see my, so if it's from a 0, 1. So at 1, if it's 0, we know that you have not committed type 1 error. If it is 1, you have committed type 1. But most of the time, it's in between somewhere. At what level? Is it at 0.5, 0.2, 0.3? At what level you will say, okay, let's accept that you are committed? Because you cannot neglect. It's not only if it's 0, if it's 1. It's just like somebody wrote exam, JAM. The person scored 400, 400. And that's it. Will he get admission? Somebody scored 400. He has passed any course because he has scored everything, 100%. Somebody that scores 0 is not like, will you help me to get course? It must be madness for somebody to be asking because the person scores 0. It cannot be. It should not even be admitted to anywhere. It's clear. But most of the time, you see people scoring in between 0 and that 400, 100%. So at what level you say somebody has passed? So many times there is just an idea that intelligent people now come with idea of 1 out of 20, 5%. At this level, which is 5% or 0.05. This is 5%. Sorry, 0.05. So at this level, they just choose arbitrarily 1. That is, if 1 out of 20, 1 over 20 is 0.05, 5%. That is, if out of 20 times you committed that type 1 error, 1 out of 20 is still acceptable. But once it's more than 1 out of 20 is big. So when your p-value, that probability of committing type 1 error, is 0.005, which is 5% or less, it is believed it's acceptable that there's a significant association. There's an association. Because what association is not by chance, there's an association between two variables. But once it's greater than that 0.05, it's believed that it's too much. From that 0.05 up to 1, forget. That should be saying the probability that you have committed type 1 error is too high. So another way of saying this, which is common, this one I just told you now is a way that makes you to understand it very well. But what people usually say that confuse many people is that p-value is the probability that the observed difference is due to chance. What you have observed is due to chance. What it means that we are looking for difference in blood pressure among between people that take more salt and people that don't take more salt. Let's say you have two groups of people. Some people take more salt, some people don't take more salt. And you will now see that for the blood pressure, the people that take more salt, they have average day is 130 systolic. But the people that don't take, that's people that take more salt. The people that don't take more salt, it give you maybe 115 average. You can see the difference, 15 millimeter of mercury. That is an observed difference. From your study, you have already seen the value. When you summarize, these people will take 130, this is 115. You can begin to say, is this salt that is causing this new? But of course, that is an observed value. You have not put it to test. We together. So the p-value is the probability that this observed value is a chance occurring. If this difference is due to chance, forget, it's a chance. If you redo it again, you may not get the same thing. But that is not due to chance, it's a real difference, not due to chance. So when the probability that is due to chance is so low as 0.05, say, I don't think this difference is due to chance, so it's a real difference. But once the probability is so high, above or close to 1, as it's approaching 1, probability is high that this difference is just a chance occurring. It just happen like that. If you redo it again, it may not even give you the same thing. It may give you different thing. Does it make sense? I think I've broken down this. Any question concerning that? So you should be able to understand that p-value concept of p-value from what I've just discussed. Any question on that? Okay, let's proceed. Now, I've just explained the p-value now, even without all these things. P-value is the probability of making one. So I've explained it. Now, let's quickly talk about confidence interval. So p-value is the endpoint of hypothesis test. So that's, if you remember, when you do your study, you say, significant, no significant, that's all hypothesis tests. So forget about the test. It's when we want to do each test now, we explain to you assumption around hypothesis test. When we want to do the test, because at the end of the day, you will see that any test, statistical test, hypothesis test, ending with p-value. But confidence interval is another differential method. Very interesting and innovative method. By the time we discuss confidence interval, you know why in medicine, if you want to publish in high impact journal like Lancet, nobody take p-value from you. Talk about confidence interval. In fact, they mess it up. They say that this p-value has no place in medicine. It started with agricultural research in industrial research in the early 90s, when they just dichotomized study into significant and not significant. It has no place in medicine. So don't be discouraged. We still use them. Because sometimes when you find it difficult to understand the concept of p-value, after you know it now, someone that says useless. It's not completely useless like that. So, but you see the superiority of confidence interval over p-value as you go. Now, let's talk about point estimate. For you to understand confidence interval, you must understand differentiate between point estimate and interval estimate. Now, we know that you as a researcher, you are interested in what is happening in the population, but you can't have access to the whole population. That's why you take sample. Now, whatever you do, you get, the summary you get, which is statistic, is an estimate of the population parameter. It can never be equal to the parameter in as much that you didn't take the whole population. It's an estimate, just to estimate it. It's an estimate. So anything you get by summarizing your statistic is just an estimate. Now, when you have your estimate, you say mean weight is 74 kg. That is point estimate. In that you are giving us one value. Or you say the average age of the student in Nine University is 19 years. Is point estimate. It's point estimate. Now, there's what we call interval estimate, because that point estimate is not so exact, it can miss it. You know that you are estimating the population parameter. For example, now if I want to ask you, and say, Farouk, your age is, you are 38 years old. If Farouk is actually maybe 36, by saying Farouk, you are 38, I'll miss it. I just guess that's point estimate. But if I say Farouk, okay, you should be in between your age between 35 and 37. I gave a range, and by that range, I likely capture it. It's a range of value. We call it interval estimate. Interval. Can you see? When you give a range of value for a particular estimate, it's called interval estimate. But when you just give only one value, it's called point estimate. Now, there is what we call confidence level in stating the interval estimate. For example, now, if I say Farouk, if I have already said that Farouk, you should be between 33 and 39 or 40. You know, that one will likely even capture it than the other one because I gave a wider range that will most likely, because even that one I gave before, you care nothing, I will have missed it. But this one I gave a larger estimate. So this larger range I have more confidence that Farouk age will be in between this 34, between 34 and 40, or between 33 and 40, than between 35 and 37. So when you give a range of value and you give a wider range that give, we now call it confidence level. So confidence, that's why in that little what called confidence interval. So the degree of confidence is confidence level and is expressed in percentage. So confidence interval now will be a range of value within which you are to a certain extent confident that the real population value will be in between. As what we are saying is that after you have calculated your mean, you have summarized your data in your sample to get your statistic, whether mean, proportion, or rate. You now calculate the confidence interval. You calculate a range of value within which you are to a certain degree, percentage confident. So we usually use 95% confidence interval. That is, I'm 95% confident that this range of value, the real population parameter, you know, I don't have access to the population. Because I've already told you what we get in our sample is an estimate, and it may not be even correct. It will not be exactly the same thing with the population. But if you now give it as confidence interval, you now give a range of value within which we are most of the time 95% confident that in the population, the value will be in between, will be anything in between the two range, in between interval. It is between the interval of the two value. That's confidence interval. And it can be used for anything, for mean, for proportion, for rate. Confidence interval of the mean or proportion of rate. Now, let's now talk about how do you get to calculate. You can even do confidence interval of the difference. And what we mean by difference, look, for example, now you calculate, you have two groups: the people that take salt, the people that don't take much salt, and you calculate, you measure their blood pressure. You see that the mean blood pressure for this group, for systolic blood pressure 130, this one 115. You can see the difference. We can calculate the confidence interval of the difference because the difference is 15. You can calculate even the confidence interval of the difference. Apart from calculating the confidence interval of each of those values, you can calculate their difference, the confidence interval of the difference. We can even say, okay, what proportion are hypertensive? Oh, among this one, I take salt, 30% hypertensive. Among this one, 20% hypertensive. We can see 10% difference. We can calculate the confidence interval of the difference. So now, this is going just to throw much light on parameter estimation. So, we talk about mean difference. So you can, if it's one sample, you calculate the mean. You can calculate if it is continuous variable, you calculate the mean. If it is that categorical variable, you calculate the proportion rate, and calculate their confidence interval. If you are talking about two groups, you can calculate the difference in the mean, different in the proportion, in the proportion. Now, all this one, they are just giving just throwing light to what we have said before. Estimator parameter. When you calculate the mean by X, you are trying to estimate mu, which is the population parameter. That's what this one just tell you. When you calculate standard deviation, variance rather, S square, you are trying to estimate the variance in the population. Now, I think I've talked about this. This is the way, how do you calculate that? Okay, before I say, the meaning of that confidence interval now is 95% confidence interval, meaning that, let's say you even somebody carry out the same research 100 times. In 95% of the time, you get your estimate, whatever interval you get will capture the true population. That's what it means. Whatever interval you get will capture the true population. That's 95% confidence interval. Now, how do you estimate it? You will have done your point estimate as you calculate your mean. You now calculate the lower border, lower limit, and upper limit. How do you do that? That one, I know in the mathematics of it is very simple, but you don't need to bother yourself about solving it. But by the time we run it, point estimate plus or minus Z. What is Z? You remember we did yesterday? We say we are looking at 95% confidence interval. You remember 1.96, the standard deviation that corresponds with the middle 95%. That is the Z score. For 95% confidence, that is 1.96, then the standard error. You remember we calculated the standard error. You see standard deviation over square root of sample size when we're talking about sampling distribution. So standard deviation over square root of sample size. And you see standard deviation over square root of sample size. That's standard error. So if you do that one, multiply by 1.96, it gives you a value. That value, when you remove it from the estimate you have made, it will give you, that is, you minus that value from the estimate, it give you the lower limit. You add the value to the estimate, give you upper value, calculated your 95% confidence. So it doesn't really matter whether you are talking on proportion or mean. All you need to do is to calculate the standard error. Once you calculate, and you can only calculate the standard error from the standard deviation. So standard deviation, you calculate the standard deviation divided by sample square root of sample size, it gives you standard error. Multiplied by 1.96, which is the Z for 95% confidence level. That is how to do it. So this one is just what I have shown you before, just to explain it, the standard deviation. That's why I put it here. Sorry, this, let me wipe out this thing. It's disturbing what I wrote on that. It's disturbing. Where is the duster now? I think this is duster. Yeah. Yes. So can you see the middle 95? This thing is still there. Can you see the middle 95? The 1.9 and 1.9, we have said it, we have done it yesterday. So just so just one just throwing light to, you see, point estimate reliability factor, which is Z, 1.9 is the standard error. So when the point, when you remove this from this, here you had it, so it give you, just giving an example. And let's just move. So this one now is telling you, if we were to take 100 different samples and compute 95% confidence interval for each sample, then approximately 95 of the 100 confidence interval will obtain the true value. That's what I said the other time. That is, we have to take some 100 times, 95% of the 100 confidence interval will get the population value capture. So these are confidence interval of mean. Can you see? Proportion, the mean is easy for you to bet. The proportion a little bit, but you don't need it. Once you just know the logic, the most important is to know how to use a computer to run it. The question I want to ask you before we close up on this section is, look at it. This, we have this diastolic blood pressure plotted. The horizontal line is the mean value of the diastolic blood pressure. And they take 6 samples and they give the, can you see the X bar, which is the mean, then lower limit of confidence level and upper limit. So how many of them included, how many of the 6 capture the real population value? Out of the 6, how many? Who we talk? On MOOC and on Muta talk. How many of them?
4.
4. Yes, you're right. So it's 4. You see the number 1 and the number 4. because they didn't cross the line. The real population value, this is the line, the mean. So if you look at all of them, somehow they capture the mean at any point, either in the middle or at the side, but they capture the mean, the population value, 4 of them. But only this number 1 and the fourth one up here, they did not capture. So it's just demonstrating in confidence interval. If you take sample 100 times, 95 of them should cross, while 5 of them will not contain population value. That is the meaning of 95% confidence interval. Now, the criticism of the p-value. The p-value, why people prefer confidence interval over p-value? P-value give you only, there are 3 things you want to know out of those 3 things to conclude about your study. The p-value give you only 1. The confidence interval give you all the 3, including the one that p-value give you. So why bother yourself with p-value? So whether, if you look at it, there are 3 things: estimate of the difference you are looking at, whether or not the difference is statistically significant, then the range of value within which one can find the population parameter. So look at it, estimate of the difference, confidence interval give you, the p-value does not give you. Whether or not the difference is statistically significant, both of them give you. Then the range of value within which one can find population parameter, confidence interval give you, the p-value does not give you. Can you see now? So that's why confidence interval is superior to p-value. Now, the relationship between them. Actually, if something is significant with confidence interval, it will be similar with p-value. It's not as if we give you different value. If something is significant, it's not significant with p-value, it's not significant with confidence interval. It's only that confidence interval give you other information. P-value does not. So 1T or 2T test. Here, I just put this one here. You may need it. You even need it, not that you may need it. When you are doing tests, you are looking at difference between 2 groups. The issue there is that if anyone can be high, for example, now, blood pressure between the people that take much salt and people that take no salt, it can be possible that even the people that take more salt have lower blood pressure. Who knows? If salt intake even reduce blood pressure. So when you are doing 2 things, you just want to see, is there any difference? The difference can come from any. It may be that the people that take more salt, they have lower blood pressure, and it's statistically significant. It may be that the people that take less salt have lower blood pressure. So whichever way, anyone can be higher than the. That's the meaning of 2 things. But there are some situations where it doesn't even make sense for it to be in both directions. But there are few situations like that it can only be in one direction. If, for example, there are some I've staggered at, but I've forgotten. But I usually fabricate one. If I'm taking statistical, I say, okay, one I've fabricated long ago is that imagine you have some women, they are still giving birth, where their first daughter is also pregnant. No, they are pregnant. The first daughter is pregnant, and both of them they meet in an antenatal. They go for antenatal. Now imagine if you are to gather women that go for antenatal, who's their daughter also. First daughter go for antenatal at the same time. If you are to estimate their age, you want to see, is there any much difference in their age? Averagely, which one should be higher? The mother's age will be higher. There's no way you say the mean age of the daughters are higher than. No, the mean age of the mother will be higher. But the only thing is that difference is significant. Is it because it may not be significant because a lot of mothers at the age of 16 they are giving birth. It's where they do early marriage. 15 you can give birth. So as that person is C30, which you can see give birth now. The daughter also can follow. The first daughter you give birth at 15 also is pregnant. So sometimes you may not see any significant difference in the age, but we know that the mother will be averagely higher than the daughter. But we just want to know if the difference is significant. In that way, it's 1 thing. We are not saying is there any difference between. We want to say, are the mother significantly older than the daughter. So it's one thing. We already know that one group is older, is higher than the other. They just want to know if it's significant. It's different from when you say, is there any difference in the age of rural and urban women that come for antenatal? So urban can be higher, averagely, rural can be higher, averagely. So that type is two things. But when it is only one direction, it's one thing. Any question? Any question? So now I wanted to know, because time is going on, we go quickly because I thought I would be able to finish this one. Give assumption. That one is the slide is not much, but I will not do that. Let's just go to our practical session tomorrow before we start, because we have 3 days, long 3 days to do chi-square. The chi-square is a lot of tests are under chi-square. Like we can quickly tomorrow fix that one before we go to that chi-square. Now, let's somebody share share that skin lesion. You still, yes, somebody, okay, thank you, clapping. Who is share skin lesion? Who is ready? Asma, are you ready? Is your skin lesion there? That data said the skin lesion. Who is share? So that I will tell you what to do. Onoja, have you installed it now? Is it working? If you are talking, you have to unmute, because I will not hear you. You have to unmute if you are talking. Edebo, you are not there. So who is here? Dr. Miller,
I'm here, sir.
Okay, have you installed it?
Yes.
Okay, that's great. So can you share your skin lesion? Or you are not?
Okay.
Okay. So you might have opened it, you might have opened it, or open your SPSS first. You can, before you share, then you can go and look for it, or you have already looked for it. If you don't open a window, you won't be able to share it in Zoom. So you can open your SPSS. If it's open, you can share the something, and now go to where the skill lecture is.
Okay.
So somebody, okay, it's clapping.
It's saying you have to allow me to share.
Okay, sorry, let me do that. You know that. So you can now. You can now.
Okay.
That's great. Okay, make it white so we can see it. Maybe yes. Thanks, man. So you go to file. You want to open it? Go to file. Go to not new. Open. Yes. Go to data. Yes. Open data. You have to know where you put it. You know where folder you save it.
I'm not sure. Let me.
It's nice. If you are not sure, who is sure, so that you share your own? Because I don't want to, because you will not learn it only if it's me that is doing it. So that's why I prefer you. That's why I share all the document with everyone. So no, you should be able to those that arrow that go up in the document, click on it, you'll be able to know where you save your. It's not that one on the right side. That arrow, no, right up, yes, that one. Click on it. To be able to know where did you put it.
I think I put it in my downloads folder.
How can you be working from download? Yeah, you can stop sharing. Let who is share? Another person to share.
Okay.
Stop sharing. Who is share? Maybe Dr. Miller, you don't want to share. Maybe Dr. Dimas share with us. So since people don't want to, nobody want to share. Dr. Dimas share, please. The more you share, the more you understand. Is Dr. Dimas there? You have to unmute if you are talking. Maybe he's cooking. So nobody want to share.
Well, me, I would have shared, but I'm not using my laptop for the Zoom. I was unable to
Why
download
won't you
it. So,
use your
except
laptop?
I'll just use my video or like screen, using my video to just show the screen.
So if everybody is doing that, how will if I'm using my phone, will I be able to project? Be showing all
Sorry,
this?
sir. Tomorrow
It
I'll
shows the
struggle to
level
do
of
that. I've
seriousness
been
this thing.
struggling.
Okay, nobody is worthy enough to share except Onoja. MSc class. Who is MSc class?
So I've been joining with my laptop, but today my laptop died, so I'm trying to turn it back on. It's messy.
Okay, Captain. Abbas,
Yes.
Asma, are you not there? Okay, let me share my own. Musa
Let
Aisha.
me try.
Oh, Mutar, okay. Mutar, you have share. I will tell you what to do. There is no big deal in this thing. Share, I will tell you, click. That's the only way you can learn this thing. It's not coming up. Is that green arrow. Yes. That green arrow that is sharing. What's happening? Okay.
In progress.
Okay, let me even my own self now. Okay, I think I've opened. Okay, let me share my own. So you can see. So I didn't even close this since yesterday. We did all this thing. Let me try to. If you look at it, the last thing I think we did was to when we select these people that are 30 years and above. So if I want to go back, if you look at it, it's still selecting them. So what if I want to go back? I will just go to data. I will now say select case. I will now say all cases. That's the default. I just say okay. So if you go back there, let me show you. If you go back there, you see that it has removed all those things. Now, I want to do some exploration here. Yeah, we have yes, okay, we have talked about normal distribution, skewness, or whatever. Okay, there's something. Okay, let's go to that analyze. We want to explore this age. Analyze descriptive statistic. Under I go to explore. In the explore, you put age. So in the statistics section, just leave it the way it is. You say plot. You see by default, you see stem and leaf there. I want to histogram. I want to put histogram also. Normative plot with text. Let's leave this option. Let's just see. Let me share the output because you will not see it. So you can see the output of what I've just done. You see, it gives me the mean. The mean is 33.2. It's also give me the standard error. It gives me 95% confidence interval. It gives the lower boundary, lower bound, upper bound. It also gives me 5% trim mean. If you see the 5% trim mean is 32.78 as opposed to the mean 33 point. You know, I want to ask you now, You see the mean, we see the median. So you see that it's skewed. It's somehow skewed because is it skewed to the right or skewed to the left? I want you to talk. The mean is 33.2, the median is 32. Is it skewed to the right or skewed to the left? At least if you cannot share, you can talk now. You can unmute and talk. Is it skewed to the right or skewed to the left? Just by looking at the figure.
Skewed to the right.
Yes, it's skewed to the right because it shows that there are some outliers that are big. So it made the mean to be greater than the median. Now, you see 5% trim meal mean is 32.78. What it does is that upper extreme value, 2.5% extreme large value, and the 2.5% extremely lower value, you remove them and now calculate the mean without them. So you know those are the outliers. So it will trim out extra the outside 5%, and I only use middle 95% of the data set to calculate. So in that situation, the effect of outlier is reduced. That's why you see it's 32.78. That's trimming. You see the median, you see the variance, you see the standard deviation, you see the skewness, you see the kurtosis. So normally the skewness is supposed to be 0 and kurtosis 0 if it's normally distributed. The skewness will be 0, the kurtosis will be 0. But in a situation where the skewness, if let's say the skewness is not 0 but it's negative, that shows that if it let's say skewed to the left, the skewness will be negative. The value will be negative. The kurtosis, if it's extremely flat, flat-curted, the kurtosis will be negative. But it's peak. Number one is peak, and it's also skewed to the right. Now, there's this, all these things I'm just still talking about skewness. There are some other, okay, let me just look at that. Look at histogram. We talk about the histogram for it. So if you look at it, if you want to, this histogram now, if you want to include the polygon, frequency polygon, remember we talk about frequency polygon. I can double click it and the extension. Graph. I want to include the I just want the graph to come off the anyway, it's hiding under
Sorry, your mic is muted.
You. I just discovered that the audio is. When did you hear me last? Please talk, please.
Like 5 minutes ago.
5 minutes. 5 minutes. I just discovered, and
Yes,
people
sir.
didn't talk that you cannot hear me. I just discovered, I don't know, the audio was okay. What I was explaining, from where? From where? What was the last you had?
After you showed the histogram, you said you want to find was it the polygon or something? From that
Okay.
point, you need.
Okay. After this one, right? You had me explaining this.
Yes. Yes.
So box with stem and leaf. I know I've explained stem and leaf. It's the same thing. It's only that this one is tilted on the side. It's the same thing with histogram. They give more information because the data set is here. You can write it out. You can write like now. We have 19, we have 19, we have 18, 19, 1, 9, 21, 23, 23, 23, about 8 of them are 23-year-old. We have 24, about 4 of them, then 4 of them 25. We have 26, about 6 of them, 5 of them 27. No, this is stem and leaf. I think you don't have problem understanding that. And they had said this one is what we call quarter plot. What it does is that there's a normally distributed data set inside the software. So what is now, they now divide them into the 4 quarters. Our own also divide it into 4 quarters and now plot it against one another. The quarter value to plot it. You know, I said that in a tug of war, if the forces on both sides is the same, the rope, they will stay in the middle. They will not cross the line. So the same thing. If, let's say, the way this one is normally distributed, the one inside the computer, which is represented by the horizontal expected value normal. If the one for our data is the observed value, horizontal, the other one is vertical. So if this our own is equally normally distributed, all these value will be on this diagonal, line on the straight line on this diagonal. Then because it's not normally distributed, you see them off the diagonal. It show, and more on the upper side, means that it's skewed to the right. If let's say more of this is on the left side, it will be skewed to the left. Then I now talk about this box and whisker. I said in box and whisker, you have the box, the lower part of the box correspond with the 25 percentile, first quarter. The upper part of the box correspond with the 75 percentile, which is upper quarter. Then the middle of the body, the line in the middle correspond with the median. So if let's say it's normally distributed, the line in the middle will be in the middle of the graph, but it's not in the middle. But the fact that it's more on the upper part, it means that it's skewed to the right. Can you see now? So even from here, you know that it's skewed. It's not normally distributed. If it's normally distributed, this line, the median, will be exactly in the middle. Then the lower part of the whisker is the lowest value. The upper part of the whisker is the upper highest value. Then all this one you are seeing some dot with number. It's just showing you the outliers and the position of the outlier in your data set. If I say, this outlier, which one is this position, the highest, which is 139, you go to, if I go to the, what do I call it? I can go to the, what do I call it? The data editor window now. It's going to be number 139 is the one that has the highest value. The one that has the lowest value is going to be number 141. Can you see? 41. I will go and check it. Let me just finish explaining all this. So I now came to this one, test of normality. You know, all this one I will say the mean is higher than the median. It's just, we're just saying with eye. We are looking at the histogram. Oh, it's skewed. All these ones skewed. They are not verifiable. They are not quantitative. It's not quantifiable. So the intelligent people now quantify that normative, whether it's normally displayed or not. You carry out a test. The two tests you use here is Kolmogorov-Smirnov and Shapiro-Wilk test. In Kolmogorov-Smirnov, you see that both of them, they are not normally, they are significant. Because what they do in the test is to test that data set they have in the computer that is perfectly normally distributed. They now compare it with our own to see is there any difference. If our own is perfectly normally distributed, there won't be any significant difference when you compare them. But because our own is not normally distributed, when you compare it, you see some significant difference. That's why the p-value in SPSS, the p-value is SIG. I don't know why they use the word significant. They don't use the word p, probably it's significant. SIG. When you see SIG, that is the p-value. It's normal because p-value is different from significant. P-value is like, what is the score? The significant is the significant level. So your p-value, the significant level you set it maybe 0.05. So that is what you use to judge it, which is the significant level. This is the p-value now. The p-value, if it's 0.01, you know that it's less than 0.05, is significant. So when you see SIG, it means the p-value. It doesn't mean that it's significant. That is what they use in SPSS inside the output. Now you see, both the Kolmogorov-Smirnov and Shapiro-Wilk test, they are significant. It shows that this thing is skewed. Does it make sense? Now, let me check. Let me go to data editor window, because I wanted to show you about. Let's go to number 41. You see, that's because the lowest, that will be the lower value of the age. (41). Can you see? 18. Can you see? Because the lowest is 18 years. So can you see? That's why it's showing you is an outlier at the lower side. That's why it's showing it in that graph. Then the one that has the highest is number 139. You see, it will be 139, the age is 56. The highest age is 56. So that's way to maneuver. Now, the next thing I want us to do, then maybe we will not stop here, is for us to, I wanted to, now, how do you explore for, apart from normal thing, how do you correct if there's normal bed? In the next slide, I'm supposed to, the lecture, that short one, we talk about how do you handle a situation when something is normal. So quickly talk about that later tomorrow and do correct for the normality here using you can use what we call logarithmic transformation. We talk about transformation. We'll transform this data that is skewed. By the time we transform it, it will be less skewed. When we plot, you see that it's transformed. But we need to talk about that transformation issue. You know, the logic, the reason for transformation tomorrow. So from tomorrow now, from tomorrow, and it's going to be more of, let's talk more practical, because when we finish that one, we start our, what do I call it? It started a chi-square. We start, all those data sets I gave you, will be running them. I will tell you which data set we are using. For each of the questions you see, if you come up, each of the questions will come up. We run the something. We go through, we run the data analysis and interpret the result. Any question? Any question? So it's good for you to lay your hand on, if you know, go and install this thing. The video, I send it to Dr. Dimas on Telegram. It's easier. If I put it on my view, you don't watch. I have over 200 of this video now in my YouTube handle. They are there. The one I've given before, all those things, they are there. My YouTube, just Google Draw Dolapo YouTube is there. You see all of them there. So you can actually watch some of them. This one, I send it through Telegram because it's edgy. The only Telegram that can, WhatsApp cannot carry, even with the email, Gmail, still, it will be, say, send it to disk or whatever. But this one with Telegram, you can easily download it and watch it and store it on your computer. So any question? I don't like it when there's no question, because we use any question, no question. Do this, you will not do. You don't ask question, you don't respond. So it's some of you are cooking. So to confirm that, Kashim, are you there? Samira, you are there on mute. I say I'm there.
Yes, sir.
Why didn't you talk? What of Dimas? Dr. Dimas, are you there? It's not there. Abbas, Asma, you are not there. So Mercy, you are using to.
I'm here, sir.
So I'm here now.
Yeah, I asked you to this. You didn't. I said you should share. You didn't share. So Mercy,
I can
you are
share
using.
now.
No, time has gone. We are not sharing
Okay.
again. I say Mercy, you are using two vessels, right? I see
One is
MSC
my phone,
cars.
one is my laptop.
Okay. So I think we close here. If there's no question. Tomorrow it will be a Top Gear. Okay, somebody shouted. Okay,
Thank you, sir.
Okay, thank you. Good night, everyone. Yes.
Thank you, sir.